Okay, so vector functions and space curves. What is that all mean? Well, we're going to set up a function, but the function is going to be a function of vectors. And so just for general purposes here, so we've got a vector function. So it's a vector, but it's a function of t. Well, the way we do that is basically we just make the components of the vector functions themselves. So this is a function, this is a function, but they're components of the vector. So the I component, I mean, we could write it, the vector function is I times f of t, or f of t times I plus, in this case I just got j. So, you know, we'll use those interchangeably. I think most of the time you see it with this notation. But so that would be a two-dimensional vector function. Then, of course, you can go over 3 dimensions or 4 dimensions, how many ever want. So we're going to talk about these a little bit here in the next few moments. So let's start with 2 dimensions, since that's obviously usually easier to get a handle on. So let's just start with an example. All right, so I've got r of t equals, it's going to be t squared. So the first part of it is t, the second part is just t squared. So visually, what does that mean? Well, one way you can think of this, if we think of kind of graphing out a few of these anyway. Let's just graph a few of these vectors that this forms. Like if I've got, well, t equals 0 is not very interesting, because that'll just give you 0, 0, so it's just the point. T equals 1, okay, so that would give us a vector, what, 1, 1. T equals 2 would give us the vector 2, 4. And then t equals 3 would be the vector 3, 9. And on we could go, and then we could, you know, it's, I guess t, you might think time, but we're not limited by positive or negatives here, unless it tells us, but we could go backwards to t is -1, so forth. But if you think about that, all right, so if we graph each of those, like I said, 0, 0 is not really a vector, but yeah, each one of these is just a vector. Position vector, whatever you want to call it. And so 1, 1, that technically speaking would be, or we could draw it in the standard position. So it's just the vector 1, 1, right? 1 horizontal, 1 vertical. 2, 4, okay, so that would give us another vector, 2, and then the vertical is 4, so something like that. And then 3, we're up at 9. So we're up at a different vector here, right? So one way you can think of that, as far as the vector function itself, it's just these moving vectors, if you will, right? Moving or stretching, or however you want to think of it. Where, in this case, each vector just keep getting longer and longer, so forth and so on, okay? Now, that's usually not how we graph this. Well, the way what we do is we usually connect, this is where the space curves come in. What we usually do then is connect that with a space curve, they call it, because ultimately when we get to, we're going to 3 dimensions here. So that's, in this case, we can still do it at 2-dimensional. And so let's sketch the space curve with this, it's called the space curve with the position vector. When we just do the same one since we got it kind of handy here. Well, what space curve does it say? Well, what you do is really you just think about the terminal points. Basically what you're going to do is, okay, so the space curve that this is defined by this vector function, it's just going to be the terminal points, which on 0, 0, the terminal initial point, all points are the same. But then the second t equals 1 point for this space curve would just be the 1, 1 point, and then the 2, 4 point for the next one, and then 3, 9 for the next one. So you get what I'm doing there? Just the point that goes along with the space curve is just the tip of the vector. All right, so this one gives me this. And then if you followed it backwards, t equals -1, what would happen if t equals -1? We'd have -1, 1. T equals -2, we'd have -2, 4. So you can see that this one's actually just going to be just like a parabola. Okay, so this is the space curve of that. And they usually reference that as C for curve, I guess. But another way you can think of it then, all right, so this is our vector function. And what is C there? Well, if you think about it, C is really, if we go back really how we did this, C is just the curve of the, from the parametric equations, the x value is t and the y value is t squared. So C is that curve just by with those parametric equations. That's what that space curve is. And so the connection between vector function and space curve, that's what it is. But technically the vector function is this series of vectors. And I just drew in the energy ones, but there's that vector, it's progressing steadily out. There's vectors in between that, which, Anyway, all right, with me there? Okay. Well, let's go to, all right. So what happens in 3 dimensions? Well, here's how they kind of show it if I've got 3 dimensions in general. So, space curve C here, it's going to be the curve, all right, so let's, just, if I did just a generalized, if I just did one vector here, just pick a t, well, each r of t here is going to be something like, say that t equals 1, that's what we got, all right, so that's our R of 1, or R, maybe I shouldn't call it 1, but you get the idea. All right, so that's one of them. Well, if I put all those kind of together and then just use the end point, if you will, of those vectors to get the space curve, then let's say R0's out here. So R1's here, so it goes somehow to here, and then it maybe, just kind of drifts off, however, and then we can go backwards, but, it's just winding around or whatever it's doing. Okay, depends on the functions, right? Yeah, so that's the same idea. Same idea in each. Let's just call that R of X. Or no, not R of X. RT. So that would be X, Y, Z, or whatever. It's just a point that comes out of that. Anyway, hopefully you kind of see the deal. All right, well, let's do some specific three-dimensional examples. We're not going to do a whole lot of these. We'll do some more graphing, talk about some more graphing of three-dimensional things. We did the plane and I guess in a line, but we'll do more later on. But let's just talk about a couple of sort of simple examples, I guess. All right, so let's sketch the curve with vector function R of t equals t, 2t, 3t. So this is a vector function, so it's just a series of vectors, but this is one just to sketch the curve that comes out of that. And again, the curve C is, it's just going to be the curve with the parametric equations x equals t, y equals 2t, and then z equals 3t. What does that translate to in a three-dimensional system? What would that be? Those series of parametric equations. It's just a line, isn't it? X equals t, y equals 2t. That's parametric form of a three-dimensional line. And of course, t equals 0, we got 0, 0, 0. So these all put together here, that's just a three-dimensional line. We've got 0, 0, 0. What would be x is, if t is 1, we've got x is 1, y would be 2, and z would be 3. So we've got 1, come out to 2, and then up to 3, somewhere like in there. So anyway, it's kind of hard to draw in 2 dimensions there, but yeah, it's just a line. That's not in the YZ plane here. It's kind of an angled line because it's coming out here, and then so it's angled kind of into the board, if you will. Like I said, it's hard to draw 3 dimensions. Hard to draw 3 dimensions in 2 dimensions. So yeah, sometimes you just get things you know what they are. In this case, it's a line. But of course, you can get a lot more interesting graphs. So let's just talk about one or two of them. Another one of those. Is that okay? Any questions on that? Look okay? All right, so let's sketch curve with vector function. R of t equals cosine t, comma sine t, comma t. A little more challenging one for sure. But we know this curve is the curve with the parametric equations. X equals cosine t, y equals sine t, z equals t. Yeah, so obviously that one's not going to be in line. But let's think about it. One way to get at this one. All right, so it is 3 dimensions ultimately, but let's think about it. All right, so what if I just did 2 dimensions? In other words, don't factor in the z dimension yet, the kind of the height of it. If I just looked at it in y and z, x and y, forget z, if you will, for a minute. Kind of the view. This would be kind of the view. See there for it. This would be kind of the view of overhead, looking at it directly overhead. Okay. So view from above. X equals, so it'd be just the x and the y. X is cosine t, y equals sine t. Well, does that remind you of anything? Well, one thing, x and y are limited to 1 to -1, aren't they? You're not going to get anything beyond 1 or -1 in both directions. Maybe this will help you too. All right, so at t is 0, I'd be at 1, 0, wouldn't I? T. At pi over 4, I'd be at square root of 2 over 2, square root of 2 over 2. Yeah, it just kind of circles around. It's a circle. It's the unit circle. Radius is 1. That's a terrible circle. Do as I say, not as I draw. Okay. Is that a little better? Maybe. Okay. Now, so that's just looking at it from the top. If I factor in the z value here, so the z value, all right, so at, let's think about it here. The best way to, why am I mislabeling my axes here today? It's Wednesday, I guess. All right, so at t equals 0, I'm out here on the xy plane. So I'm right on the x-axis. No no y value. The y value is 0. So let's expand a little bit so we can leave. And then the t value is also 0, right? So I'm at 1, 0, 0. So that's an easy point. Okay. 1, 0, 0. Now, let's jump out here. This is t equals pi over 4. Well, what does that do? Well, so it's square root of 2 over 2, square root of 2 over 2, comma, pi over 4, right? So the point over here, I'd be at, so at t equals pi over 4, I would have square root of 2 over square root of 2, square root of 2 over 2, square root of 2 over 2, comma, pi over 4. Well, all right, so this thing is spinning around, but what's happening? It's getting height to it, right? So this point's at 0, but the next point comes in, if you're thinking about z as the height, so the next point comes in, or a point farther along, it comes in at this xy value, but it's a little higher, right? So it's up here. It's spinning around, so it's not in the xy plane. It's now up here at a height, whatever the z value is. So at pi over 4, that kind of gives me the height. So it would be square root of 2 over 2, square root of 2 over 2, but the height would be pi over 4, which is, what's that, about 0.75-ish? So it's up here. Now, when I get at pi over 2, I'd have, what would it be, 0, 1, pi over 2. So I'm at 0, 1, but it's at a height of pi over 2. So it's up here at pi over. So I've come around, it's come up, and then it's at a height at pi over 2, it's up here at a height of pi over 2. So it's kind of just, like I said, it's hard to draw here. It's coming up, progressing up. All right, then it circles back around, but the height just keeps getting bigger. Then it's going to circle around, height's going to keep getting more and more. And it's going to circle back around. I don't know how good I'm doing this here. And then if we go backwards, it does the same thing. So what you get is, it's a helix. If you look at it overhead, it's kind of, this might help. If you look at it overhead, you're still seeing it's kind of a cylindrical shape, right? But point by point wise, it's progressing up that cylinder. It's not the cylinder. We'll talk about how we graph a cylinder, but this isn't a cylinder. It's just the helix. It's how I guess kind of the path a bug would take if it was climbing up this cylinder here. What are we thinking? It's a helix. Okay, so you get some interesting things with these vector functions. Anyway, they're fun to think about sometimes. All right, any problem or concern here? Yeah, they have a nicer sketch in the book there if you want to peruse that. Okay. Now, good news is we're talking about a function, right? Vector function. And so this is our first taste of kind of some calculus stuff. We've just been kind of getting geared up, I guess you might say, to do some calculus in our little course here. Now we can begin here talking about some calculus. Limits, derivatives, integrals. We can do that. We're going to do that now. But the good news is, a lot of times, doing these three-dimensional things, or I guess vector functions could be two-dimensional too, but there's a lot of analogous stuff to what we previously did in our other calculus endeavors. So that's good news, right? First of all is, if we talk about the limit of a vector function, so limit of vector function, so we've got r of t vector function. Well, good news is, all right, so r of t is just as a vector function, so the components of which are just functions. What if I do the limit as t approaches an a r of t? Good news. The limit of such a thing is just the limit of the component parts. It's going to be a vector function itself, but the good news is, yeah, you just do the limit as t goes to a of the x component, the limit as t approaches a of the y component or j component. So that's good news, right? You just have to do the limits. As long as you do the limits of those individual parts, that's the limit of the vector function. So that's pretty sweet. Now, bad news is, or the catch is, you got to remember, you know, how we do those limits. Those things will come up a little bit. This first one's not too terribly bad. All right, so let's find, let's say we got RT equals 1 plus t cubed, t e minus t, and then sine t over t. what's the limit as t approaches 0 of r of t? Again, it is good news because all you have to do is you do the limit of each individual part as t approaches 0. So let's just denote that way. Well, sometimes they are nice to us. You know, the limit as t approaches 0 here, well, there's no trickiness to it, is there? Just plug in the 0, right? That'd be 1 plus 0. Here, that limit would be 0 times e to the 0. There's nothing indeterminate about that. The only tricky one is the last one, right? Because what do we got here? Well, I'm not going to be able to figure this out because that's 1, that's 1. Sorry, 0. 0 times 1, which is 0. But here I get 0 over 0, don't I? Indeterminate. So sometimes you run into those indeterminate, and we like when we run into 0, 0 because that's L'Hopital, isn't it? So I got to do the limit. Let's just put it this way: sine of t over t. So to do this limit, I've got to use L'Hopital. So you got to get 0 and 1. I'm sorry, 1 and 0. So you got 1 and 0. But you got to do the L'Hopital here, so it'd be the limit as t goes to 0. L'Hopital, you do the derivative, so it'd be cosine t over 1. Now we're good to go, aren't we? Cosine t, the limit as t goes to 0 is 1. Divided by 1 is 0. All right, so could run into something like that. Now, again, just to make sure that you make a connection there, that's one form of it. If we wrote it in the IJK component format, it'd be 1i, so it'd be just I, 0j, so we don't even have to write that, plus 1k. So, I mean, it does look fairly different, but those two are the same. We could write it that way if we wanted to. All right?